this mistake. So we are going to continue because I stopped at the point where we just graphed those functions in polar coordinates. We noticed that it's easier to graph in favorite XY called rectangular coordinates, right? They said Descartes coordinates. Descartes, René Descartes, French mathematician that lived in 1700 and created those Descartes coordinates. Question is, what coordinates they used before Descartes? Was it polar? Nobody knows. But anyways, looks like they do have some importance, but definitely not everything is convenient to graph in polar coordinates unless you have functions of the circular nature, like the one that we graphed last time, the rows, and some others that are in a way similar to them. So I want to now add the story of calculus to what we saw last time. I deliberately decided not to overload you because the section contains quite a bit of material. And we're going to recall the story of parametric equations and how we can apply them to the case of polar coordinates. So the standard way to call functions in polar coordinates is R, which is some kind of a function of variable letter theta. So they actually take this and rewrite with favorite polar coordinates that we parametric equations that we already utilized in the previous section. So x is arc sine, actually the polar coordinates, sorry, and y is r times sine of theta. So that's polar coordinates presentation of the coordinates, right? So x, y convert to polars, actually from polars to get x, y. And then replace r with function, whatever it is, in terms of the functional relation here. So we got a f of theta times cosine. So just plug in. And for the other equation, it's going to be, again, r is replaced with f of theta times sine. And we can see that this turns into a pair of parametric equations of parameter theta. So this little substitution gave us ability now not to have just polar coordinates, but the x of theta and function y of theta. So our parameter become theta. And then we can use our old formula, not too old, but the one that we utilized a few class meetings already. So we need to take derivative of the first product and derivative of the second product. And we know that derivative of product is derivative of first times second plus derivative of second times first. And that's exactly what they're doing here. So you can see they put this on the top, derivative of y. And then on the bottom is derivative of function x. And this actually composes the derivative of the function that is actually given in those parametric equations with respect to parameter theta. And it's function for X and for Y. So it's in polar coordinates, because the actual thing here, as you can see on the graph, is not a function, but relation. But we have utilized its coordinates separately. So we utilize the approach of functions. So that's a little trick that worth noticing. And then they try to find the tangent to this function at, since it's in polar coordinates, radius or r, the distance to the origin, and theta is the angle, right? We can get points in that format. So that's what they actually produced. But one could say, if I had x, y coordinates that I can also produce using this r and theta, these are the equations, then I could also get it. Yes, of course. But I guess with functions that we're going to deal with here, we're going to need the actual polar coordinates for convenience. So they practice utilizing these for various examples. Maybe it's worth for me to take a look at one of those examples, like they trying to graph the function here in example 5, and they want to find the key points. The key points when your derivative is equal to 0, and that's the slope of tangent line. So it looks like there'll be a couple of points that we can find. And also when derivative is undefined. So that'd be that pair of points when slope is undefined. And how we find this? Well, we're looking at the produced formula. So let me actually produce it. So it's dy dx, right? So we take derivative of y and then divide by derivative of function x of theta. So y, f prime times cosine. Derivative of cosine is negative sine, so minus f times sine of theta. I put theta. And for x, it's going to be a f prime cosine, and then derivative of cosine. I think I miswrote the second one, right? Because it's a sine here. So I think I should be careful, right? Because it's sine, so I need to have a sine. Got carried away. So then I have to also change derivative of, so I guess I better just clean this mess, otherwise it'd be messy. So it's going to be a derivative of first times second, which is sine, right? I'll put theta. And then minus actual derivative of sine is cosine, so it's going to be plus f times cosine. So that's my numerator. And then for denominator, I take derivative of x. So it's again derivative of f times cosine, and then derivative of cosine is negative sine, so it'll be minus f times sine. Okay. So when I have some kind of function which is r of theta, that's my basically function of theta, then they gave us this function which is a sine here. So I need to take the derivatives and set this in this format. Then notice that my slope is going to be equal to 0 when my numerator is 0. So when f prime sine theta plus f times cosine theta is equal to 0. And of course, since my function is given as a sine theta, then I can utilize that f prime as cosine of theta. So you can go ahead and replace here the cosine times sine plus f is going to be a sine times cosine is equal to 0. So looks like sine cosine plus sine cosine, it'd be 2 times sine cosine. Is equal to 0, or we can say this is the sine of 2 theta, isn't it? Are you familiar with this formula? 2 sine cosine is sine of 2 theta, one of the favorite formulas from trigonometry. If you don't remember it, then you can split into 2 equations and solve one for sine equal to 0 and the other for cosine equal to 0. But I think one equation is better than 2, so my sine is equal to 0 and sine is my y coordinate, so these 2 points, and that's why 2 thetas is equal to pi times n, and then theta is pi over 2 times n. So what does that mean here? That we have these special points, pi over 2, and then pi over 2 plus pi over 2, which is going to be a pi, and that's point that corresponds to pi. Or if we have a 0 for n, that's going to be 0.0, and so forth. So it looks like at this upper and lower points that I put in the pink, we have the result. One say, well, what about these? Well, these have nothing to do with my graph because these are actually solutions of that equation with respect to theta. So now, once I found the angle theta, then I utilize that. And then also, so my derivative is equal to 0. Now for these green points, we have those two, where derivative is undefined, which means that denominator is 0. You see? So my denominator, which is this stuff, f prime cosine times. So you get a feeling probably that these are not very short exercises, right? They're quite tedious. F prime cosine minus. So I need to be careful and we'll get it. Just, I guess, need to get a piece of paper and pen and you will get it faster than I'm sure. So we set it equal to 0 to get those points where the tangent is vertical. And again, f prime was a cosine, so it'll be cosine times cosine. And function f itself was a sine, so it's a sine times sine. So it's cosine squared minus sine squared. Does that look familiar? That's for double angle, right? It's a cosine of 2 theta is equal to 0. And cosine will be 0 for, since it's x coordinate, for points pi over 2 minus pi over 2. So I can say that 2 theta is pi over 2, and I can say period is pi times, that's how I can describe these points. Again, it's up to you how you describe the points, as long as you describe them, and you might describe it with 2 equations, but at the end of the day, you will get exact same result anyway. So I take a half of everything. So I'm carefully doing little algebra and get the pi over 4 plus pi over 2 n. So it looks like period is exact same, but now we are going to have angles such as pi over 4, and then another pi over 2 will be 3 pi over 4, and another pi over 2 will bring us back again, and so forth. So we get those planes indeed. So it's nice to realize that we can graph now using methods of calculus. So the key methods of calculus, finding maximum, minimum, and also in addition to it, we find the tangents on the left and on the right. And that's what they're doing in these exercises, but you can see there's quite heavy simplifying processes, and that's, well, I guess nothing you can do but just enjoy it. So the formula that really excites me in terms of graphing is here, theorem 1012, that actually says the following: if our R equal to 0, f of alpha, that's R, right? So if R is equal to 0, in other words, we have a pole. No matter what angle is, we're here at the 0 point. Then the line, which is tangent, is going to be a tangent to the graph. So the line where the angle, whatever we have, makes this function equal to 0. So function means radius is 0 at that point. So for example, they have picture here. So there is a graph of this, and all of a sudden it comes back to the R equal to 0 or to the pole. Then the line, that angle that we have where R is equal to 0, they call it, let's see, alpha, is going to give us a tangent line. So the function, in other words, will be tangent. So it's not going to go somehow around this. No, it's going to be exactly coming to that pole. And that's very big help in graphing. That's what I actually utilized last time, and that's what we kept on utilizing for granted in trigonometry class, and that's all because of this theorem that gives us nice ability to graph. So why does it work? Well, there are two conditions. First of them is that value of function is 0. So if you look at the derivative above, notice that this piece disappears because value of function is 0, and so does the other piece. Now f of f prime will cancel, so we just end up with sine over cosine, and that's a tangent. So why is that going to be the actually tangent line? Well, that's how we presented our derivative, right? So that's what we do when we have the tangent line. So the actual, remember, y over x, the opposite over adjacent, that's going to be a tangent of that alpha. And that's the line that they're talking about. So that's angle alpha. So that's worth to give a little thought how it works. And of course, I didn't mention the other condition, which is important in here from algebraic perspective, because if it equals to 0, then the whole thing is not going to make sense because we get 0 over 0, so it can be just anything, right? So you want to make sure that this derivative is not 0. We're not using it though, but making sure so they can cancel those, because otherwise 0 over 0 we really don't cancel, right? It's some indeterminate form. So we want it not to be equal to 0. And this theorem helps us a lot in graphing. And we'll be using it all the time when graphing. We already used it. So at that stage, they just conclude with that section, and they have various little exercises in it. And well, they just continue doing the same thing that I did last time, but with a little extra, you can also find the special points where we have tangents that are vertical or tangents that are horizontal. But technically, we never cared about those when we graphed anyways. So those are is little extra that I don't think we are utilizing. But the idea of graphing, I think, is explained here. And I want to add one more thing. I don't want to tonight talk about the entire next section, just to give you a little bit of intuition into the next step that we will see here in finding the areas. So differentiation for the functions to get those minimum maximums, and also the points where the tangent has undefined slope. That will be helpful when you say why we never actually looked at those points where tangent had undefined slopes when we took calculus class. Well, because we worked with functions, and now we're not working with functions because this is not a function, this is relation. So we make it be function, remember, by turning x coordinate into a parametric function of angle theta, and same with y coordinate into parametric function. And that's what enabled us to actually start dealing with them. And that's what added extra part to the story that we learned, not just maximums and minimums where derivatives are zero, but the points where the derivative is going to be undefined. So it's interesting, I think. But anyways, the next part of the story, integration, that usually is dealing with the areas. And they come up with this formula that I think is interesting from geometry. If you have the, for example, circle with radius r, then its area is pi r squared, right? Whenever you have circle, there are two formulas attached to it, pi r squared and 2 pi r, the circumference, right, like perimeter. So pi r squared is area of the whole circle. So what if you take a part of circle with angle theta? Let me make it bigger so you better see it. Angle theta. So some part of circle. Assuming that this side is radius and this side is radius. Well, notice that if angle here was 360 or 2 pi in radians, then angle here will be, so notice for that whole thing, then angle that I'll use here in analogous formula for the area will be a half, because what I utilized, notice, not 360, which is 2 pi, but half of it, pi. So analogously or proportionally, if my angle is theta, I take a half of it. So I get a theta over 2 times r squared. That's interesting to give a little thought why this works. And then we can split any region with these little sectors and split them in such a tiny little way that each of the sectors will be pretty much same as a portion of a circle with radius r, and that radius is given to you by the function that describes this in terms of r function of theta. So the role of r will be played by function of theta, because indeed r is function of theta. And then, since we are going to have so many little pieces, then taking a limit, we actually are going to deal with pieces of circle. So that's what makes it be useful. So we're now going to look at the formula that we take that angle delta theta, this tiny little theta, multiplied by 1/2, and also multiplied by square of this function. So that's really same thing that we just had. And since we split it into n pieces, then we take a sum sigma from 1 to n, and then we take also the limit with respect to n that approaches to infinity to get an exact area. So standard setting for the integral, and to find the area, we're going to have definite integral. So if we start with angle alpha and end it at angle beta, so we go integral from alpha to beta, and then either you put the square of function or just square of r, and a half is going to be in front. So the formula for the area, and that's what we actually, I guess, justified. So the area from one angle to the other, because again, function is with respect to angle theta, that's the variable, and we have to take a square of this function of theta, and of course d theta, that's our variable. So that's the area of not a sector of circle, but sector of whatever curve that you can imagine. That's quite interesting, right? So you can now find areas of various chunks of these curves and polar coordinates that convenient to describe this in polar coordinates, and that are not functions in xy coordinates, but happen to be functions in polar coordinates, functions of variable letter theta. So if you take a look at one of the examples, I guess today I just want to read the example, and that could be good enough. And next time we'll do some examples on our own, because I know this is a little different compared to what we used to have. So in example 1, they have the function r, which is 3 cosine of 3 theta. Okay. So now we need to set this formula to find the area of that single petal of our rose that is in between of negative pi over 6 and positive pi over 6. Let's see, why is it negative and positive pi over 6? Well, let us just find it, and then we can justify why is it negative and positive, because turns out that when that's our angle alpha, then remember the value of function at that angle is equal to 0. So you find these poles when we graph. Remember, we graph our maximum, our minimum, and r is equal to 0. That's important because that's for poles. So you solve equation cosine 3 theta is 0, then you get various values of multiples of pi over 6 plus, looks like, pi over 3 theta. So anyways, we'll get the function r squared. So I'm going to set it up from minus pi over 6 to plus pi over 6. And there'll be a half always in front. And we're going to have r squared d theta. And function r is of theta. Notice that it's more convenient to calculate the integral from 0 to pi over 6. Again, depending on the function, but I think that 0 usually works better. So if I have this split it, basically, this petal split it into 2 pieces, right? So one is in between angle 0 and the other in between pi over 6. And then the other is going to be the same, so I'm going to have to take it twice. And there's 1/2 in front will not nicely cancel. And then I need to square my function here as well. So that was cosine of 3 theta, which I square. The theta. And then question is how to find this antiderivative of cosine squared of 3 theta. And looks like we need to utilize the formula for the double angle. So cosine squared alpha was divided by 2, 1 plus cosine of 2 alpha. Again, all of these formulas are in front of the textbook, the trig part. I think we barely looked at them when we looked at the trigonometric integrals, and I know that they're hard to memorize, but well, I guess we need them for this case. So once I utilize this formula, then what we got is this 2 and 2 canceled. So we're going to have just a 9. Notice they are taken not from 0, but from minus pi over 6. That's why they still have that half. And now they integrated. So I guess you can see how they found antiderivative. They plug numbers in and ended up with some type of a number. And I guess if we use 0, then we'll have something a little different, but double and you get same result. So the message is that to read solutions of examples sometimes takes time, and it takes a little bit of extra work to really understand what is going on. And that's why what I'm doing right now is showing how to read the calculus textbook. I think that's very important, especially if you're gonna take more mathematics, because the textbooks have tendency to skip steps. As you can see, they skip in here a bunch of steps, such as the explanation why all of a sudden, instead of this square, they got something over 2. So because they use the double angle trig identity, and they didn't even mention which one, they just said trig identity. But anyways, so they do skip steps, and here they're nice. They trying to explain, but sometimes they don't even bother, especially when you take a higher level mathematics classes. There'll be more steps skipped, more and more. So sometimes it might take you a week to read just one page of that textbook, because there'll be so many symbols that to understand what they mean, you need to figure out from some other sources what they're talking about, and it takes a while. Once you already get into it, then you can start to read it a little faster, but they utilize other knowledge. And in fact, if they produced a nice book and some type of abstract algebra course, they would probably have like a big encyclopedia instead of 200-page book that actually consists lots of material that they assume you know from prerequisites. And that's the, I guess, tendency now to produce math books for higher classes. And that's why you really want to read it with piece of paper and pen, and basically to write everything down and figure out what steps are skipped, and then you start to understand. Otherwise, it's just pointless. So anyways, I think that I'm not gonna give you a quiz here, because it looks like we just started this last section that we need to cover. So on Monday, I will continue with section 10.5, and you can actually enjoy some graphing of these functions that talk about polar coordinates and graphing. And maybe I can do one problem for you, and that would be good enough, and let you go without a quiz, because I think you're already familiar with it. Maybe I'll do number 55. That's a little bit unusual curve, 55, because these kind of things usually bother people. And yes, that's a good idea. So what I'll do is, let me write 55 down, then I'll tell you what homework, so I don't have to return back to the same page again. So let me get some room for that. So I just want to graph function in the polar coordinates, and turns out, even though this section contains some calculus in terms of derivatives, don't use it. You're basically utilizing the ideas of previous class of trigonometry class to do all of the exercises here. And again, I hope you are familiar with this, but I know that if you don't use it, if you took the class a year or even more than a year ago, then you might have a little bit of a hard time with something that is not really related to calculus, just trigonometry. But it is a basis, of course. So anyways, I'll be graphing this function, but I was asked to first refer to what sections we covered since the midterm, and I think this is a great question. Makes me very happy. It means that you are planning to actually do some homework, and I think it's a good plan and good timing. So we started at the end of chapter 8 for the midterm. We were looking at the L'Hopital's rule, right? So 8.6 was disregarded. So L'Hopital's rule, section 8.7, that's a big story. And then we also did 8.8 improper integrals. That's another interesting section. Then we went to chapter 9 and we did everything up to power series, but we skipped Taylor stories. So it'd be like 9.1 and 9.6 through 9.6, so 9.1, 9.2, and so forth. And then we looked at 9.8. So our class is now 4 units, so we skip on these sections. That's disappointing, but those sections have lengthy exercises, so some people got help. Then I also disregarded 10.1. This is something that I guess you should already know, and started at 10.2 and went through 10.5. So that's our homework for the final. So the final is going to be on Tuesday, week after next. I believe it's May 2nd. May 2nd. So next week, we're going to do plenty of review for that final. I will send you practice final. So I'm sure you will be happy with that review, just like we did with a midterm. So let me graph. Yes, you're welcome. We definitely should be able to do this. So now here's the exercise 55 that talks about r squared is equal to 4 sine 2 theta. So notice that it's r squared. R squared is always non-negative. And that's the key part to observe, that our sine 2 theta must be non-negative. So when you're looking at the sine function, the angles that I want to consider are those in between 0 and pi, and then again starting from 2 pi and so forth. Notice theta is multiplied by 2, so it's not that straightforward. But the point of story that we're going to be only concerned with angles that correspond to positive values of sine, positive values of r, of sine, sorry, because r squared is always positive, could be 0, but so sine has to be greater than or equal to 0. And that's actually what I'm gonna try to solve this for. So I'm gonna actually find when sine 2 theta is equal to 0, but we'll keep in mind range of that function. So then 2 theta, since our sine is y coordinate, then we care about points such as pi, 2 pi, 0, and so forth. In other words, pi n, and therefore theta is equal to pi over 2 times n. So now I have found when r is equal to 0. Remember, we found these so-called poles. And when we have angle of pi over 2, which is 90 degrees, then we have a pole for the function. So the function will somehow come to this pole. So it's going to be tangent. And also the same thing will happen, that's angle pi over 2, when angle is 0, because when n is equal to 0, we also have a pole. So when angle is 0, let's say theta is equal to 0, or like x-axis, the graph is also going to be having a pole. So the point is that this is going to be a piece of graph right away that we produced, but I think I should be a little bit more tangent to the y-axis. So let me graph it a little bit better. So it has tangent here and also has tangent here. So it's going to go somehow like that. And looks like in between, where angle is pi over 4, I'm probably going to have my maximum value of r. So what is r maximum? Well, that should be 4 times 1, right? Because the largest value sine takes is 1. So which means that sine is equal to 1. And indeed, sine of 2 theta is 1. This function is 2 theta. That's why our 2 theta sine is 1 at angle pi over 2. So 2 theta is pi over 2 plus period, of course, 2 pi n. But theta is pi over 4. Let me get some room. I'm trying to fit it all here. It's not a good idea. So theta is pi over 4, just as we already guessed. You see, these problems you can do a little faster rather than just calculate all of these points, and it takes a little time. So anyways, the next and important part is that one that I just erased, that we don't have a graph here. From pi over 2 to pi, we don't have a graph because our sine 2 theta will be negative. So the other part of graph is here. And this is graph of so-called lemniscate. And that's the one that usually people make mistake on. They start to graph some stuff here and there, and that's not the case because we have only positive value for sine. So I really wanted to do this exercise, and as I said, I'm gonna let you go. I know the weekend is coming. We had plenty of those quizzes already